So students, in this video, we review the Esscher Premium Principle. Escher was, I believe, a Swedish mathematician, and I hope I pronounce his name approximately correctly. So the principle is stated here. Recall we are trying to define a premium, an insurance premium to cover the insurance risk, big X, here a random variable. This principle says the following. If this exists, which you could say is the MGF of X, for any little h here, and h will be an important quantity here that is positive. So if the MGF exists there, then you can define the premium as follows. It is a ratio of expectations. On top, you have expectation of x times e to the hx, and then on the bottom, similar thing, but you don't have the x in front. So it's just expectation of e to the hx. We now spend a bit of time to try to understand why this principle makes sense. The global explanation is this. What we're doing under this principle is that we transform the original distribution of the risk, the original distribution of X, into a new distribution. This new distribution is riskier because it allocates higher probabilities to large outcomes. And then we take the expectation of this new transformed distribution, and this is the premium here, pi x. Now here, this explanation for now is not so clear. We need to unpack that. We need to show that indeed, another way to state this is as the expectation of a riskier version of x. So we spend a bit of time on this interpretation now. Just a comment that the principle here applies generally. You could have x be a discrete random variable or even a mixed random variable. But for the explanations that follow, we narrow our scope a little bit, and we're going to explain the principle, assuming for now that x is fully continuous. This way, the mathematics are a bit simpler. For example, you can have that big X as a density function. So we will denote here simply little f of x. This will be the density function of x. Now we define this newer version and riskier version of x, which we will call x tilde. So x tilde, this is another continuous random variable that takes value in the support 0 infinity. We define, so we choose this, we define its PDF to be here g as follows. Now, note that it's a function of x here. And on top, you have fx, to which you multiply e to the power hx. On the bottom, what do you have? You have this integral, but you see this integral as no x. So this, you can view it as a constant. Again, because here you define a new density function of the argument little x, and there's no little x here. Now, let's first agree that this function is a valid density. Maybe you can take a second to convince yourself it's the case. It is the case because for this to be a valid density on the support 0 infinity, it means that the integral of this density from 0 to infinity with respect to dx, this needs to be equal to 1. But it is almost trivially the case here because, as I said, the denominator here, the yellow bit, doesn't have any x. So when you take this integral, you can just take the integral of what's on top. And then what's on top and what's on the bottom exactly identical. So of course, this is 1. Okay, this shows that gx is a valid density. Okay, so we have then defined a new random variable, x tilde. Now a bit of work to find the expected value of this x tilde. Well, this is what is done here. Expected value of x tilde, well, as usual, you just integrate the density from 0 to infinity. The density, of course, multiplied by x. Now, gx is there. You have this bit that's, again, a constant. There's no x there. And you have the other bit here. But now look at what is on top. Now everything is you can see it as the density of something times the density of x. So because you integrate on the whole support, something times fx, you can say it's the expected value of that thing where the random variable here is x. Well, yes, because this f is indeed the PDF of just x, the regular x, the initial x. But then on the bottom, this part, it has always been the expected value of e to the hx. Same logic. You are simply integrating on the whole support something function of y here times fy. But again, this little f is the density of x. So you can say this is the expected value of this e to the hx. Okay, and then you look at this. This is exactly the premium as defined in the previous slide. This is exactly this. So this highlights what I said earlier. The premium defined here, you can say is the expected value of some random variable x tilde, and x tilde is the random variable with the density over there. Now we still need to explain a little bit why x tilde is a riskier version of x, and this is what the next slide is doing. First here, there's a little bit of terminology. If f is the CDF of x, then the CDF of this x tilde is called the Esscher transform of f with parameter h. Because again, h matters a lot here. I mean the numerical value that h takes. We're going to explain that in a second, but for now, just view h as just a constant. But if h is 0.001, it's quite different than if h is 0.1, and it's different than if h is 1, etc. Okay, this bit is just terminology. As I just said, the Esscher premium pi x equals the pure premium expectation of x tilde, of the risk x tilde. But now, for the interpretation, the PDF that we call gx is adjusting the PDF fx by an exponential factor here, e to the hx. And this obviously alters the likelihood of every outcome little x. Well, yes, remember that the density is represents the likelihood that a certain outcome x happens. So if we start with fx here, and we multiply it by something, in this case, e to the hx, in this new density that we define, we have modified the likelihood of any specific outcome little x. Now, yes, you are also dividing by the yellow bit here, but again, the yellow bit has no x there. So this is a constant. You are dividing every you are dividing the density at every point by the same constant. So in the interpretation, we don't really need to consider the constant there. What really matters is the multiplication by this term e to the hx. And of course, h is positive, so this thing is positive, but more than that, this, of course, is an increasing function of x. Said otherwise, our adjustment here is an adjustment that's bigger and bigger, the bigger and the bigger the values of little x get. Said otherwise, we are allocating a bigger weight to extremes outcome of x. So if you compare x to the newer version x tilde, the newer version x tilde has extreme value. By extreme, I mean big value, strongly positive. Those values have a higher outcome now. A higher likelihood of occurring in the case of x tilde. That is to say, the Esscher transform results in a fatter right tail for x tilde. Again, because, well, a fat tail means that very large outcome have some non-negligible probability to happen. So what's happening here is that the Esscher premium loads the pure premium. Pure premium, I just mean here the expected value of x, by assuming that x is heavier tail than what it actually is. So conceptually, what happens here is that we know we want to charge a premium that's bigger than expected value of x. How do we do this? We assume x is heavier tail than what it actually is. this would be the x tilde, and then we take the expected value of this one, which will be bigger than the expected value of x, and that's our premium. Yeah. Now one more property, one example, and then we're gonna systematically check our axioms, because again, in this lecture we have presented axioms, 5 desirable properties for our premium principles, and then now with our newest premium principle, the Esscher principle, we will check if our axioms are verified or not. Spoiler alert, 4 out of 5 are going to be verified, so that's not too bad. Now one comment here, you can easily get the MGF of x tilde as a function of the MGF of x. This is done here. You see the MGF of x tilde, you write it here, start with the definition. Now you can write an expression for this expected value because you have explicitly the density of x tilde over there. So this is what you use. You have the expected value of this. Okay, this explains the term here. But then the density of x tilde, remember, it's the e to the hx times fx, yeah, that we had over there, divided by the yellow bit. Again, the yellow bit is a constant in the sense that it does no x. So you have this, and then simplifications. You can regroup this term and this term together to be e to the t plus hx. But then you look at this, take a second to convince yourself that this is just the MGF of x evaluated at the argument t plus h. Yes, and on the bottom, you have, again, the MGF of x, but evaluated at the argument just h. Okay, so this gives us a pretty simple expression for the MGF of x tilde as function of the MGF of x, which is quite convenient for calculations and proofs. Now, an example. Assume the specific case where the initial risk is exponential. Find the Esscher premium pi x for this risk x. And then you can assume that h is smaller than lambda. Now, there's a very simple way to do this, which is to use this property here. We find the MGF of x tilde. Now, spoiler alert, x tilde is again exponential. And if we know x tilde is exponential, we very easily find its expectation. So let's just review that. That's the MGF of a exponential with parameter lambda. So use the formula we just saw. You're gonna have your MGF evaluated at t plus h. So we have, well, you have the lambda, and then you evaluate that the argument t plus h. On the bottom, same thing, but you evaluate at the argument h. Now simplifications have happened. This cancels this. This goes on the top. And now you look at this expression. It's again the MGF of a exponential. Only the parameter now has been updated. The new parameter is lambda minus h. Well, yes, look at the form of this. It is exactly the same as the form of this. It's just that the lambda has been updated to a lambda minus h. Now, to make sure this is defined on the correct support, you note the following. Here on the top, we needed t plus h to be smaller than lambda, but that, if you rearrange, just means that t is smaller than lambda minus h, but t smaller than lambda minus h is exactly the correct support to make this a valid MGF of the exponential. Okay, and so we conclude, yes, indeed, x tilde is an exponential with a new parameter, and that's the trick. We know that the premium is the expected value of the transformed version of x. So the premium is the expected value of x tilde, and mega easy then, we know that the expected value of an exponential is 1 over the parameter. Again, careful, we have a new parameter, and so we see straight away that this is going to be bigger than the expected value of x, which is 1 over lambda. So I hope that was understandable. And now let me just take a sip so I don't lose my voice. And my Mr. Happy mug also reminds me to be happy. Okay, now we go ahead with the properties. Again, we check by properties, I mean the axioms. We check if they hold or not. The first one is actually the hardest to prove, non-negative loading. So again, this just means that the premium cannot be smaller than the expected value of the risk. That makes sense overall. And I kind of said that this should be the case because I said that x tilde is riskier than x. So we expect the expected value of x tilde, which is the premium, to be bigger than the expected value of x, but we haven't proven it. So now we spend a bit of time to do it. Now the first thing to note is that if we have h equals 0, and now technically in the premium principle, this is not allowed. We said h must be strictly bigger than 0, but let's assume for a second, if you add h equals 0, then you would have that the premium is exactly equal to the expected value of the risk. Well, yes, because if h is 0, e to the 0, that's just 1, so it's not there anymore. On the bottom, same thing, e to the 0, that's just 1. Okay, so you would be left with just the premium is the expected value of the initial risk x. Okay, so if h is equal to 0, here they explain it in a different manner. The MGF are the same, so the expectations are the same. And then the trick is that we will show that as long as h is strictly positive, pi of x is an increasing function of h. But this then proves the result, because what we have is that if you visualize here pi x is a function of h. So here, to make that clear, I'm going to add a little h here. So the premium depends on the specific h you have. We just said that if h is 0, then the premium equals the expected value of the risk. But then after that, this pi h is some increasing function of h, which means that for any h, pi x must be bigger than the expected value of x. So this is what we will rely on for the proof, or at least that's the proof technique. I'll just say here that it's actually quite useful to know that. So regardless of the proof of non-negative loading, it's quite useful to know that pi h is an increasing function of h. Okay, now for the proof. What we do is we will express the moments of x tilde using mx, and after that we will see that because here we under the assumption that we know the random variable x, if we have expressed the moments of x tilde as a function of mx, we'll be able to show that that e of x tilde is an increasing function of h. But first things first, expected value of x tilde to the power k. So here k is a positive integer. So we were just taking the kth non-central moment of x tilde. Now, we use the well-known property that if you take the derivative of the MGF k times, and then you evaluate the MGF at the argument t equals 0, that gives you exactly the kth moment. That's a well-known property. So we do that, and next we use the trick presented before, that the MGF of x tilde, you can easily express it as a function of the MGF of x in the following manner. Now here we have our h here, and on the bottom we have the h. Now here, this derivative is with respect to t. So this thing here has no t. There's no t because we've plugged specifically h in the MGF. So this term, the denominator, we can put it in front of the derivative. So we put it here. Then we are left with this. And here, from here to here, I hope this step is not too esoteric. We do need to take a moment to convince ourselves that it's valid. We are kind of magically changing the derivative to be here. You see it was with respect to t. Now we make it with respect to h. That sounds a bit weird at first, but when you think about it, look at this function. It's just the good old MGF that you evaluate at t plus h. But so inside this function, you will have t plus h everywhere. Everywhere, I mean that the initial argument is. So if you take the derivative with respect to t, it will give you exactly the same thing as if you take the derivative with respect to h. Because you have the simple argument t plus h, when you apply the chain rule, because you would if you have just the first derivative, for example, you derivate this with respect to whatever argument, either t or h, and then after that you derivate what's inside. So you derivate this with respect to t or h. But of course, derivating this with respect to t or h gives you 1. Okay, so the chain rule here doesn't do anything for us. Because of that, you can indeed rewrite that this derivative, if you rewrite as with respect to h, exactly the same thing. Okay, if it's still a bit mysterious, this step, give yourself a specific example. Write this to be the MGF of your favorite distribution, say exponential, because it's quite simple. Take the derivative with respect to t, and then take the derivative with respect to h. You're going to get exactly the same result. It has to be here. Maybe I'm making this too complicated. It has to be because t and h play exactly the same role here. They are interchangeable. And also the chain rule doesn't give you anything. My point with the chain rule is that it's just that if you had, say, t squared here, then you couldn't do this trick. You couldn't just change the differentiation to be from t to h, because then chain rule here will give you, when you derivate this with respect to t, you're going to get 2t. And then when you derivate with respect to h, you're going to get just 1. So that wouldn't work. But here, because we have just t plus h, it works. Okay, hopefully we're convinced that here we're not doing any sort of forbidden things. And what happens then? Recall that this step happens after you do the derivative. Meaning the meaning of this thing is that you first differentiate this, and once you obtain your whatever this expression is, then you evaluate it for t equals 0. Okay, because of that, once you have this, you then evaluate at t equals 0. So this thing, everywhere there's a t in this expression, the t just is 0. So then you're left with just the derivative. You're left with just the derivative of mx, but now with respect to h. Okay, so in the end, that's the final result. Kate moment of x tilde is the initial MGF of x, derivated h time and evaluated at h, and divided by mxh. That's the main ingredient we need to show what we want. And again, what we want to show is this, that the premium is an increasing function of h. How do we show this? Next slide. Now, the premium is this, okay? Remember, expected value of x tilde, this is our premium, okay? That is function of h. Okay, and yeah, I hope this is clear that this premium is function of h. And so then it makes sense to take the derivative with respect to h. And if this derivative is positive, then we have shown what we want, which is that the premium is an increasing function of h. Let's do it. Derivative of the premium. Now, the premium, we just showed that the first moment of x tilde, we could write it like that. Here it's just the special case where k is 1. So it's the derivative of mxh divided by mxh, but we take the derivative again. So now here we apply the rule that the derivative of a ratio is like that. Derivative of this thing is this thing times the denominator minus this times the derivative of this. But so then we have this times this. Well, the derivative of this. So we have derivative of mx, the first derivative square. Okay, and then everything divided by the square of the denominator. Now this is just the derivative rule for ratios that we know from high school. Then some simplifications, yes. What are they? Okay, yeah, this is the derivative of this part. So we have an mx here that cancels one of the mx here. So we're left with second derivative divided by mx. And this one, because you have a square here, you have a square here, why not put everything together? And why we do that is that now we recognize, because of our property that we spent some time obtaining, this thing is the second moment of x tilde. Oh yes, you have the second derivative of mx divided by mx. So here, if you look at that, second derivative would give you the second moment of x tilde. And here we have the first moment of x tilde, again using this equation. So first moment of x tilde square, well, we have this. What is this? The variance of x tilde. This is the variance of x tilde. A variance is positive. And here we write strictly positive because we made the assumption earlier in this lecture that x is non-degenerate. Okay, so x takes is not a constant, right? X is properly a random variable. So if x is a random variable, x tilde would also be a random variable, meaning it's not a constant. So its variance is not zero. It has to be strictly positive. Okay, we've done it. Okay, that's really the end of the proof, because then this last step is just saying what we're just realizing what I just said. If h is 0, the premium is just the pure premium, expected value of x. But then for any other h, you know that the premium of x, or the expected value of x tilde, is strictly bigger because of this, because we've shown that the derivative is positive. So it has to be that the premium is an increasing function of h. Okay, we've done it. And then, yeah, then we check the other properties, but I promise they're not as difficult to show than this one. I mean, this was not that hard. I hope you agree. But the other ones are even simpler. Okay, let's go. Now we have just shown non-negative loading. We will show additivity, consistency, no ripoff. Let's go for additivity. Additivity means that the premium of the sum should be the sum of the premiums. You write just the definition of the premium for a random variable that is x1 plus x2. Okay, so this, the first step is just the definition. Then you see this x1, you can multiply it by this, and then I have a separate, and then I have the plus the other term, this one times this, and then imagine in your mind this times this. Well, the x1 times e to the h x1, this is here, but then this is then times e to the h x2. But e to the h x2, because x1 and x2 are independent, then you can take that the expected value of the product is the product of the expected values. This is why this is separate here. E of blah, blah, blah times E of this. On the other side, it's going to be exactly the same thing. X2 times, well, this, the E to the H x1, you put it outside, and then you're left with E of x2, E to the H x2. Now, by the way, I'm just this, okay? This obviously is not equal to E of x2 times E of H x2, right? Because obviously x2 and E to the H x2, they're not independent at all, right? Because they're a function of the same x2. So in the exam, I don't want to see this, okay? This one, I do not want it to be simplified as the product, okay? The product of an expectation is the expectation of a product is the product of the expectations only if the terms are independent. Okay, sorry for the side note. And then you're almost done, because of course on this side, this will cancel this, so you're left with this. On the other side, this will cancel this, so you're left with this, and you're done, because by definition, this would be the premium of x1, this would be the premium of x2. Okay, not too bad. We move on to the consistency. It's similarly not too hard. By definition, the premium of x plus a constant, you have this, this, this. Then what happens? The term here e to the hc would go outside. Same thing, the term here over here, term e to the hc goes outside, so those cancel out. Okay, so you're left with this on top, this on the bottom. Then what happens? This times this, that's the term that's over there. And then, yes, then this times this in the, maybe I should write it explicitly. If you have expectation of c to the e hx, the c obviously is a constant. You can put it in front of the expected value. Okay, but then on the bottom, you have exactly this. This is why we are left with a c over there. And again, we're done because we recognize this is by definition the premium of x based on this principle. No ripoff, easy as well. Start with the definition of the premium. Now, just replace this one by xm. Recall xm is the upper bound for x. Okay, so x is always smaller or equal to xm. So then this is why you have this inequality here, because you see this thing is always smaller or equal to this thing, because the only difference is the x that you have replaced by a quantity that is the absolute biggest value that x can take. Yeah. So, and this works also because this is strictly positive. Yeah, strictly positive, and this is strictly positive. And then you're done because, of course, this is a constant. You can put it outside, and then whatever remains cancels out. You get to xm, and that you're done because you've shown that indeed the premium must be smaller or equal to the upper bound of the risk. This is the 4 principles that hold, but unfortunately for the fans of this principle, the last axiom doesn't hold. This was the scale invariance. We can check that relatively quickly. Scale invariance doesn't hold. Scale invariance, remember, would be, we would like to have the premium of a constant times the risk. We would like this to be the constant times the premium, but it's not the case here. Why? Well, let's write first explicitly what this premium is. In the general statement of the premium, you just replace x by a times x. So a times x is here, a times x is here, and a times x is here. But now I've put in a specific color this thing h times a, because here we have a as a constant that is not 1. Well, because the case a equals 1 is kind of trivial. I mean, it's trivial that pi of x equals, you know, I mean, pi of 1 times x, of course, will be equal to 1 times pi of x. Okay, so this case is not interesting at all. This is why I've written a is not equal to 1. But now look at this. This is a constant. Okay, it's a positive constant. H times a is a positive constant. So you can just call it, here I just call it h star. And so we are left with this. And now here we write this is not equal to this. And this is, of course, just the premium of x. Now, why is that? Why do I say that this blue thing is not equal to, let's change colors, this yellow thing? Do you see? I'm claiming here without any further justification that this is not equal to this. Well, the reason is the proof we spent a bit of time working on, because you see, this, you could call it the premium of x, but under the case h is h star. While here, this is the premium of x under the case h. But we have just said that the premium is an increasing function of h. So you see, if h star is bigger than h, then this thing, this one is bigger. And if h star is smaller than h, then this premium is smaller than this one. And of course here, because A is not 1, they're not the same. H star is not the same as H. So H star is either bigger than H or smaller than H. So in every case, this does not equal this. Hopefully that's clear enough, and that completes the proof, because then you have indeed inequality. You have this is not equal to the A times the premium of X, and that's it. You have invalidated this axiom. Okay, we're done. We've covered this section. So I'll stop here. And you will no doubt send question our way on the discussion forum if you have any questions. So thanks so much for listening. See you hopefully in the next video.